what I have decided still to elaborate a little bit about this example with symmetries. Remember I mentioned last lecture that everything, all these kind of conceptual issues related to symmetries can be actually clarified using very simple example of just circle. So let me spend still 5 minutes, although I ask you to do this, but let me still, because that will be important for our discussion. Now, so I start with some remarks on symmetries. And so I was talking on very clear example. Let's take circle. Clearly this is symmetric figure, right? Symmetric object. How do we realize this? So if we have some coordinates, x and y, and return the coordinates, then in new coordinates, nothing will change. You will not recognize any changes. So to say, you are sitting and looking at this way, but then you turn your head, and circle will be circle. Ideally the same as in the beginning, then at the end. So this is the same. And to realize this, you need to make some transformation, right? So you need to turn yourself, or you can turn the circle. And again, you will not see any changes. So, symmetry is invariance with respect to transformations. Certain transformations. Different symmetries are associated with different transformations. Which means that to define symmetry, means to define transformations. So introduce symmetry means to introduce certain transformations, and then to say that something is invariant under transformation. Invariance means that there is no change. You do transformation and your object is the same before transformations and after transformations. Okay? So, let me come back to this example. What I was saying, that you can turn the coordinates or turn your head essentially, right? Which means that you go from x and y to y prime and x prime, and x prime, and this is the angle. X prime is cosine angle x plus sine angle y. Y prime is cosine alpha y minus sine alpha x. So in this way we define the transformation, which is actually characterized by the angle alpha. So let me do a little bit formal, because this is simple. And again, come back always to this example to clarify some conceptual things. So this is x and y. And we can write as we did before. We can denote n prime as x and y, and n as, so prime and prime, x and y. And then we can write this transformation as n prime equals u n. Now I generalize in a sense, but you know what is behind here. And u, and this is the matrix of transformation, is given by C alpha. I write short writing cosine alpha S alpha, then S alpha minus S alpha and cosine alpha. So if you use this n prime n and this matrix u, you exactly reproduce these transformations. Okay? Now, next step, what I did, I inverted these equations and have written them in terms of y and x as functions of x prime. So, x prime is, let me again use short notations, as alpha, x prime, here is minus s alpha y prime, and y is C alpha y prime plus S alpha x prime. So I inverted this transformation law. So what I did is have written n equals u minus 1 n prime. Right? So that's equivalent to what I have written in general in this way. Now we are talking about invariance, and the circle is, and let me put it as H, because eventually we will talk about Lagrangians. Let me take this in the form x squared plus y squared. And this is a question for circle. Okay? Now, I take H as a function of x and y, and insert here expression for x and y in terms of new variables using this equation. So, if you insert into this equation x and y expressed in this way, what you will get? You will get x prime squared plus y prime squared. Check if someone is in doubt. So, this is invariance, which means that our function, our Hamiltonian, or the circle, equation for the circle, has the same form in the old initial variables and in the new variables. And this is invariance. Invariance means that equation which describe our Lagrangian or circle doesn't change its form, shape, when you transform from the old variables to new variables. And so this is invariance with respect to transformations. And remember what we did precisely, like this. So we took Hamiltonian as a function of n, or functional. Then we put here, instead of n, its expression in terms of n prime. And then I said that if this can be reduced to h n prime, then we are saying that this is invariance. And this story will repeat many, many times. So you'll see. Essentially, this is the essence of symmetries and invariance. Questions? Repeat again if you want. Of course, if you will do some other transformations, and you can invent some other transformations. So, for instance, you can say, okay, let me introduce my transformation law in different way. For instance, I can write that x prime is, say, a times x, and y prime is b times y. Then, easy to convince yourself that this equation is not invariant with respect to these transformations. I can introduce many different transformations, but they will not let my Hamiltonian invariant. So actually what is interesting that this circle has, apart from this rotational symmetry, which is O2, and again I will repeat in the last part maybe this the same thing, it's also invariant with respect to reflection. And actually reflection is not reduced to just rotation. So we can change x to minus x. And again, you will not see any change. And so, which means that this object is invariant with respect to reflections. So remember we discussed invariance with respect to SU2 transformation, which was the isospin symmetry and isospin invariance. So in that case, of course, the transformations are not like this. They are more complicated, but the story is completely the same. So I have written here in a general manner. So n can be any multiplet or any group of the objects. So you do transformations, you introduce a law of transformations, and if you show that after transformations you have the same form of your Hamiltonian or your object, so you are saying we have a symmetry, we have invariance. So what you can say? It turns out that the symmetries, and if you know the symmetry, even though you don't know exactly the form or explicit form of this, can lead to many, many consequences which can be extracted even without precise knowledge or explicit knowledge of your Hamiltonian. And we will see this later. Questions? Remember and repeat this in parallel. So this is explicit example, and I have repeated this in more general form. And so again, this can be multiplet, it can be proton-neutron doublet, it may be something more complicated. The transformations can be much more complicated than just this rotation, but the story is the same. Let me come to what we started to discuss last lecture, and that is quarks, introduction of quarks. As I said, the quarks have been introduced in the process of classification of hadrons, strongly interacting particles. And the first step was to observe that many hadrons observed in the beginning of 60s already can be grouped. They can be considered as they are forming some families, the families of hadrons. And as you remember, a given family, as like a family name, is fixed by baryon number, by spin, and parity. And within a given family, you have different members of this family with their names, right? And so what are the names? Within the family, you have strangeness and isospin, third projection of isospin, or you can use the charge and the strangeness. Let me put this ST, and that just to mark is not the spin, because here is a spin and here is strangeness. So let me show you examples of these families. And I will put members of the families in the plot formed by strangeness here, and here in the third projection of isospin. And the first family which I want to describe is the family of mesons with baryon number equals 0, with spin equals 0, and disparity minus. Let me put minus 1. This is parity. So all members of this family have these quantities, but they have different strangeness and the third projection of isospin. Let me put also here. That's 0. That's minus 1/2. 1. 1/2. Here is 1. So we have 3 pi mesons, which is pi minus, pi 0, and pi plus. They have 0 strangeness. Now we have 4 k mesons, as we discussed before, k0, and k0 plus. They form isospin doublet. They have strangeness 1, but they have doublet. They form doublet with isospin 1/2 and minus 1/2. Now another pair of k mesons form another isospin doublet. It's k minus, and here is k0 bar. And now there is another particle which is a singlet of isospin, and which is eta. Now we can connect this and get this nice diagram. So there are 8 members of this family, and you see this is also 0. Here's pi 0. It has actually non-zero total isospin. It has the 0 third projection, but it has non-zero total isospin. While this eta 0 has both eta 0, it has both total isospin and the third projection of isospin to be 0. Another family I want to describe is the family of baryons. And now this family is characterized by baryon number 1 and spin 1/2. It's quite similar. So now I have again strangeness here, and strangeness changes from 0, minus 1, minus 2, and now isospin is very similar. So 0, minus 1/2, minus 1, 1/2, and 1. And this is the third projection of isospin. Now what we have here neutron and proton. Neutron and proton, they are sitting here, neutron and proton. So they have 0 strangeness, and they form isospin doublet with the third projection 1/2 and minus 1/2. Then the triplet of sigma hyperons has been observed. Sigma minus, sigma 0, and sigma plus, and this is analogy of pi mesons. They have strangeness minus 1, and they form isospin triplet with components minus 1, 0, and plus 1. And finally, as theta hyperons, with strangeness minus 2. Here's minus, and this is 0. They form isospin doublet. And finally, the 8th component is a lambda hyperon, lambda, which has -1 strangeness, and it has 0 isospin, both total and the 3rd component, which is an analogy of this eta 0. And again, we can connect everything in this nice way. And we have again 8 components of these baryons. Now, this is for baryons, and of course there is a similar octet with baryon number -1 when you put antiproton, antineutron, antisigma, etc. Okay? Questions? So, now I want to describe what is called eightfold wave. And of course the question is, what is the meaning that we have these families of different particles? It was also observed that these particles have the same strong interactions. So, it was an idea that strong interactions are invariant not only with respect to isospin symmetry, as we discussed before, but probably strong interactions are invariant under wider symmetry, which actually acts on these octets of the particles. So remember, isospin symmetry, it acts in this dimension, right? It can change K0 and K plus to some combination of these particles, or interchange them. The same is for pi 0. So isospin is acting here. So the same is for baryons, but again, suspicion is that strong interactions have much wider symmetry. Which is not just a transformation of isospin or rotation in this isospin space, but is rotation which actually changes particles or combination of particles within the families. So this eightfold wave precisely means that octets we observe form representation representation 8 of, or transformed under representation 8 of certain symmetry. Of strong interactions. Of strong interactions. So let me now delete this. And repeat this in more kind of formal way. So suspicion is that there is a symmetry, which we call GF, flavor symmetry. And octets of the families, which we have discussed, transform, so we can say, write that in, so the octet is 5 plus, 5 0, 5 minus 8 components. They are transformed as representation 8 of certain symmetry group GF. So let me write this as U acting on octet of mesons. Transform this octets, components of octets. Precisely as we did this with X and Y in our example. And the key point is that Hamiltonian of strong interactions is invariant under this transformation U, or it has the symmetry GF. And the story is we discussed before. So we have octet of mesons in our example. The Hamiltonian of strong interaction is somehow the functional of this M. Right? So the symmetry means that we are doing transformation, which is, we can write M as U minus 1 M prime. Insert in this expression, so you have U minus 1 M prime, and Hamiltonian of strong interaction is invariant, which means that it has the same form in terms of M and M prime. So now this U is 8 by 8 matrix, right? Because we have 8 components. And our symmetry transformation is 8 by 8 matrix. So it's 8 by 8 complex matrix. Okay. Question? Now the question is, what is this group GF? So you need to find a group which has representation 8. And for instance, SU2, it has representation 8. However, in this group, inside the multiplet, you will have charges, say Q0, Q0 minus 1, Q0 minus 2, Q0 minus 7, which certainly doesn't match to what we have, because we have this pi 0, then K0, K plus, K0 bar. So here the charge is changed by one unit. So SU2 doesn't work. And the next what we can try is to use SU3 group as the symmetry group of strong interaction. So in this case, octets of particles transform under 8 representation of SU3 group. And actually what is important is that the symmetry group of isospin was SU2. And SU3 of course contains SU2, which is nice because in all these multiplets we have also particles which are connected to isospin symmetry, which means that the symmetry GF should include the isospin symmetry, but it should do something more. Another point is that particles inside the multiplets are characterized by strangeness and isospin. So there are two physical consequences, two physical parameters to all operators eventually in quantum sense. And I also mentioned that actually these quantities, these operators correspond to diagonal operators of the symmetry group. I was going to show this in the third part of the course, precisely when we develop all the formalism of the symmetries. Not now, but if you want, I can elaborate this maybe later. This lecture, maybe tomorrow. So this means that we need to have some group which has two diagonal generators. So to say, we need to have the group which has rank 2, not just 1. And then these diagonal operators can be identified with strangeness and with isospin, and therefore characterize the particles inside the multiplet. So it's again, SU3 is good because it has two diagonal generators. SU2 already for this reason fails because it doesn't provide description of strangeness. And strangeness is some characteristic which characterize the particles inside the multiplets. So let me remind you about properties of SU3. So fundamental representation is 3. You had SU3, right, in your group theory course. Okay. Then we can construct high order representations, and in particular, and this is complex. That's also a group of complex matrices, 3 by 3. So we can construct high order representations as 3 bar, and decompose it into irreducible representations. So we have 9 components, which can be reduced to 8 plus 1. And so we have irreducible representation 8 and singlet. We also can construct the high representation by using the product of 3 fundamental. So it has 27 components, which can be expanded as 10 plus 8 plus 8 plus 1. We can also use 3 times 3. And that gives us 6 plus 3 dimensions of irreducible representations. So what is nice, that we have 8 representations, which is precisely what we need to describe multiplets or families of hadrons, which we already identified. Of course, the question is, and this is a very important question, so how about this 10 or 6 or 3 or even fundamental representation? So where is the fundamental representation? Why it is an important question? You will see that there is a physical clear answer to these questions. Where are these particles which are transformed under this representation? Nowadays, in the literature, what many researchers are doing, they introduce some sophisticated symmetries, but use just some representations. And the symmetries have many different representations. And they do not use all. They just ad hoc pick up some representations which they like, and ignoring others and even don't care about this. I think this is completely wrong. At least nature likes to fill in the smallest representations. Of course, SU3 has a much higher representation. It has infinite different representations of much higher multiplicities, right? That's one story. We can discuss why. But why? What we observe, that nature fill in all minimal representations. So, and if you invent some symmetry, and for your purposes you use only few or even not lowest representation, then you must answer why other representations are not used. Why there is no other particles which are transformed under representations which you are not using. I think this is deficit, or this is kind of failure of many flavor symmetries which people are inventing in these days. And you can find in the literature hundreds of papers with this type of developments, but they ignore some representations. So again, the question is, where is 10? Fundamental, 6, and also here there's a 3. And you will see that the crucial developments related to answering these questions. Now let me start with representation 10. It turned out that the family of particles with 9 components has been discovered. So let me again depict our plot at 3. And now the strangeness is 0, -1, -2. -3. An isospin, third projection, 0, 1/2, 1, 3/2, -1/2, -1, -3/2. So, particles with baryon number 1 and spin 3/2 have been discovered. So those include delta minus, delta 0, delta plus, and even double charge particle. Double plus plus. You see, these delta resonances form quartet of isospin group. They transform as representation under representation of 4 of the SU2 group of isospin. And even we have here double charge particle. So next, with strangeness -1 is sigma minus. We had already sigma before, but this is sigma with spin 3/2. Now this is sigma 0. I'm making here spin, but so the difference is with what I have described before in the spin. And here is sigma plus. Now there are 2 particles, so they form triplet of isospin group, and there is a double of theta. I think here is 0 and here is plus. So 9 particles have been discovered, and you see it would be nice to have another particle which is sitting here, which was not discovered by the time of introduction of SU3 group. And then it was idea that probably another particle exists, so that altogether in this family there are 10 components, and then they form the couplet of SU3 group. Then it actually very nicely can be embedded in our SU3 flavor group. So this particle omega minus with strangeness -3 has been eventually discovered. And discovering of omega minus was really very strong confirmation of correctness of this eightfold weight and SU3 flavor symmetry. Questions? Are you convinced? You see, it was something like this. But symmetry already, the idea that those guys are transformed under certain representation of symmetry, gave us prediction that it should be another component here. So and everything is actually inscribed in a very nice triangle. And that has been discovered. Now, how about fundamental representation? Which is a really important question. Why nature started with high representations? Why there is no particles with the lowest of high representation? It was no hadrons with this lowest representation. How about representation? Fundamental representation. This is also related to the question that octets are 3 times 3. And also we have octets which are 3 times 3 times 3. And also we have decuplets which also belong to this product 3 times 3 times 3. What is the physical meaning of these octets as the product? It should be like that, right? As the product of 3 bar. The answer to this question has been done by Gell-Mann, by Zweig, actually who didn't continue with physics but started to do neurobiology. So he had some important contributions to this field. And Neumann, so their idea is the following. Hadrons are composite states of more fundamental objects, quarks. Quarks are transformed under fundamental representation. So, there are three quarks, which we denote as U, D, and S. And this triplet transforms under triplet representation of SU3 group. Well, sometimes we are doing, or you can meet in literature, people are saying, oh, triplet representation. So, quarks form triplet. More precise, of course, quarks form triplet which is transformed under representation 3 of SU3 group. So this is complete and precise expression of what's going on. So we have triplet of quarks which are transformed under 3 by 3 matrices which are representations of SU3 symmetry group. So, more precisely, mesons are composite states made out of quark and antiquark, Q bar, and therefore their operator, their wave functions of mesons is the product of wave function of quark multiplied by wave function of antiquark. So this is transformed under 3, this is transformed under 3 bar, and therefore the product is transformed under, say, octet, if you take just a reducible representation. Actually, we have 9 components. 8 form this family. And there's another one, eta, which is called eta prime, and there's an interesting story related to this eta, but I will not elaborate on this. So, you see, now we have explanation why we have octets. Because they originate from this product of the operators, a product of wave functions, and those are transformed under 3 times 3. For baryons, baryons are composite states of 3 quarks, quark, 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 and therefore their wave functions are the products of 3 wave functions of quarks, and therefore this product is transformed as under a representation made out of 3 times 3 times 3. And in particular, one of the irreducible representation here, octet, 8, and also 10. Well, actually nowadays also pentaquarks have been discovered, which are combinations of even 5 of the quarks. Again, so it's like a Q, 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 Q bar, 5 quarks. Usually it's very unstable objects, and I will not discuss much, but just to say that, of course, this is not the end of the story. You can compose even higher representations. Now, what are the properties of quarks? Since we want to have baryons made out of 3 quarks, clearly that the baryon number of quark should be 1/3. Of course, you can speculate that maybe some quarks have, say, 2/3, some 1/3, but you can easily convince yourself that this is the only option if you want to reproduce properties of observed hadrons. Other characteristics of quarks can be extracted from the properties of hadrons, mesons and baryons we have observed. And for this one can use the feature that electric charge of hadron, and electric charge is additive quantum number, is the sum of the electric charges of quarks entering a given hadron. So the same is for baryon number, and the same is for strangeness. Strangeness, total strangeness of hadron, equals the sum over strangeness of particles, of quarks, which enter. And the same is for the third projection of isospin. Hadron is the sum of the third projection of isospin of quarks. So using this, and you will have exercise to check, you can reconstruct what should be the property of quarks. So, we can write octet of mesons, for instance, in the following way. So, mesons are products of quark and antiquark. And we have U, D, and S quarks. We can put here U bar, D bar, S bar. And that eventually should give us pi 0, pi plus, here is K. What is this K? Let's see, it's U is plus 2/3, and this is minus plus 2/3 minus. Plus pi 0, again pi plus, and I will, so this is some combination which I will tell you. So this is K 0. This is K0 bar, here is K minus, and this is eta. So to say, I can put my 8 particles, 8 mesons in this way, more clear, so more close to the structure that it is product of quark-antiquark operators. So knowing these charges, you can find what should be the charge of individual quarks. You can do some simple algebra and to find what should be, using also this relation, what should be individual properties of the quarks. By the way, I have written here pi 0, maybe I should put here pi minus pi 0. So the point is that it should be 8 components. Here you have 9, and the trace should be 0. So that's how we put out of 9 components, because if you have product 3 by 3, you have 9. So how do we pick up 8 components? So we demand that the trace is 0. So that will give connection, and therefore you have pi 0 and eta, only 2 on diagonal. There is a systematic way, so this is for you to check. There is also a systematic way, group theory way, to establish what should be the charge, what should be the property of the quark. So we have SU3 group. And as I said, operators of physical quantities are related to diagonal generators. let me just make very quick. Some of you may know this, someone knows. So we introduce eventually operators of physical quantities. And operators acting on a given multiplet gives you the corresponding generator multiplied by Q. And since T is diagonal, if you take diagonal, then this equation will look like equation for eigenstates and eigenvalues of a given operator Q. And this is why diagonal generators are important to identify physical quantities. So, just for time being, remember this relation. And let's see what we have in SU3. In SU3 we have lambda 3 generator, which is diagonal, and square root of 2 multiplied by lambda 3 is 1/2 minus 1/2 and 0. And so this is diagonal. All diagonal elements are all zeros. Here is also 0. And clearly that we can identify this diagonal operator with I3, the operator of third projection of isospin. So in this case, U quark and D quark form the doublet, and so that the third projection of U quark is 1/3, 1/2. The third projection of D quark is minus 1/2, and third projection of strange quark is 0. And in fact, we will see it later, so it's 0. Now there is another operator, another generator of SU3 group, which also is diagonal, and this is lambda 8. And if it takes square root 2/3, then it will have the following form. It's 1/3/3. This is 1/3. And this is a minus 2/3. This can be written as 1/3, 1, 1, 1, plus 0, 0, minus 1. These components can be identified with baryon number and with strangeness. And so we see that the third quark, strange quark, has the strangeness minus 1. And U and D quark, and we are kind of considering the space formed by U, D as, U and D have 0 strangeness. And this is what we need, right? U and D are made of proton and neutron, and so they should have 0 strangeness. K mesons have strangeness plus or minus 1, and so this part we can identify with operator of strangeness. And we can write that square root 2/3 lambda 8 is baryon number plus strangeness operators. And this actually, what we introduced before, is hypercharge. SU3 group contains SU2 and U1. So SU3, it contains SU2 and U1 subgroups. So that would correspond to isospin, and that would correspond to strangeness. So now we can complete with properties of quarks. We have U, D, S, I3, strangeness, and of course we can write B and electric charge. So for isospin, we have 1/12, minus 1/12, 0, strange is 0, 0, 1, minus 1. Baryon number is 1/3, 1/3, and 1/3. You see this matrix is diagonal, and therefore everybody has the same. And now charge, electric charge, can be constructed as I3 plus B plus S over 2. This is precisely the formula empirically derived for hadrons. But since we have additive quantum numbers, the same should be satisfied for quarks. And in fact, using this and this definition of operator of electric charge, we find that this is 2/3, this is minus 1/3, and this is minus 1/3. Questions? Again, you can reconstruct these quantum numbers by just knowing that your pions, K-mesons, atom mesons, so they are composed of quark and antiquark. And then knowing electric charges, strangeness, and third isospin of hadrons, the pions, K-mesons, you can find out what should be the property of quarks. By the way, in the early days, people didn't like these charges which is not integer. And there were even models of quarks with integer charges. For a while that was kind of a competitive explanation, but then eventually it was found that the charges are really not integer, so it's even 1/3. Questions?
Professor, I have one question. When we do diagrams for families and they for children.
Sorry, I hear you, but I don't know. Your microphone has not a good quality. Because others I understand, but I don't know why say again.
Okay, when we do the diagrams for the families with baryon number equals to 1. Yeah, okay.
Yes.
We did it for isospin 3 and strangeness.
Yes.
Yeah, okay. But we could do it with isospin and hypercharge. So in that case, we can see that, for example, we can see that the neutron, and I don't know exactly what is the sign. I mean,
yeah. So
which
strangeness
is doublet,
yeah,
or not? And that's my question.
Doublet of what?
Doublet
of isospin. Proton and neutron is doublet of isospin. Yeah.
Yeah, but in hypercharge we can say that, for example, we had the Kn0 and Kn plus.
And hypercharge. Sorry, and the hypercharge is the same for proton and neutron.
Yes, but what if in the neutron and I don't know what it looks like the Epsilon, but not. I don't know the name of the.
Yeah, you can actually find out what is. So you have all these formulas. You can find using these formulas and using that hypercharge is B plus S, and you can find what is the hypercharge, and this is strangeness. of all components, also the quarks, and using additive properties. And everything matches fine. You know, what is important that characteristics of these baryons on mesons have been measured before this eightfold way, or SU3, and all these parameters like strangeness, hypercharges, all they have been already established. And what is nice, that this description reproduces exactly what has been obtained, measured, which is a great confirmation of all these things. One more comment. You see what is behind the absence of hadrons in triplets. This quark structure is a big deal, right? So the fact that we do not see the hadrons in the triplets, in the triplet representation, eventually led us to introduction of quarks. Now I can ask questions. Maybe some of you know. So remember, it was representation 6, which actually appears when we have 3 times 3. So that is, can be expanded as a reducible representation 3 and 6. So what happens with this 6 representation? Does it exist or not? So the answer which we have not yet given. So we have also representation 6 of SU3. What happens? Do we see some hadrons which form family of 6 components? And the question, why we do not see this? Why? So the answer is that we do not see hadrons. We have hadrons in 10 plates, in 8 plates, but there is no hadrons in 6 plates. Why? And one should give the answer to this question, because it's strange that nature fills in, say, triplets, okay, these are quarks, it fills in octets, it fills 10 plates, but not 6 plates. Why there is no 6 plates? And I should say that all QCD is behind this answer to this question. So we will see later that these guys do not form stable particles. They have non-zero color. Finally, we will introduce color, and we will conclude that only particles which have 0 color can be observed. 6 times 6 cannot form object with color 0, and therefore it doesn't exist. So you see how many things are just behind the answer to the question why there is no such representation or another one. So to answer, we need this quark structure and we need QCD. Okay? More questions? Good. So, we discussed already some interactions. We discussed electromagnetic interactions, weak interactions, and strong interactions, but at hadron level, at the level of pions, mesons, and baryons. But now we will do the same thing going to the deeper quark level, and we will discuss now weak interactions at quark level. And let's start with beta decay, which is transition of neutron to proton plus electron antineutrino. Neutron has the following quark structure. It is composed of U quark, D quark, and another D quark. So this is quark picture of neutron. This guy has electric charge 2/3. This minus 1/3, minus 1/3, and the whole system has electric charge 0. In contrast, proton has, let me put it here, U, D, and U structure. This is proton. So it has 2 U quarks and 1 D quark. So this is 2/3, 2/3, 4/3, and minus 1/3. You can check by just electric charge. This is already almost enough to identify. So to transform this system of quarks to this one is to transform one of the D quarks in neutron into U quark. And here one is to emit electron and antineutrino. So at quark level, beta decay is the transition of D quark into U quark with emission of this electronic pair. So we introduce hadron current, which is responsible for transition of neutron to proton. And that current looks like P gamma mu 1 minus GA gamma 5 neutron. Now to describe quark transitions, we need to introduce quark current, which transforms D quark into U quark. And we can introduce this current as U gamma mu Q, G Q vector minus G Q axial vector gamma 5 and D quark. And for lepton, as we did before, we introduce current E gamma mu 1 minus gamma 5 mu, as we did before. So it's again current times current, but now instead of this hadronic current, we introduce quark current. By the way, I have just written 3 quarks here, which usually people are calling valence quarks. So these are quarks which carry the quantum numbers of proton. In fact, the structure of hadrons is more complicated. Inside the proton and neutron, we have not only these 3 quarks, but also quark-antiquark pairs and also gluons. We will discuss this later. But those quarks are responsible for quantum numbers of a given hadron. Now we have D quark, so it can be processed when this quark emits electron and neutrino, but we have another one, and we need to take into account that another D quark can emit this. And then U quark shows like a spectator. It is not transformed, it is not affected by interaction, it's just looking how 2 other guys are transformed one into another. Now the big question is, and very important, again, it's crucial for the standard model construction, is what is connection between these constants at quark level and constants at hadron level. So the question is, what is connection between G and G quark? Are they equal or not? And there are 2 very important concepts which give answer to this question. Please take attention on this. concept is conservation of vector currents. And so it's abbreviation C, and C conservation of vector current. This conservation of vector current, and therefore the corresponding charges, so we have conservation of electromagnetic current, which leads eventually to conservation of electric charge. Here, this idea about electric situation in electrodynamics is generalized to the case of weak interactions and strong interactions. So it turns out that according to this conservation vector current hypothesis, G vector Q, this is what enters quark current, is equal, exactly equal to what we have at hadron level, and this is 1. So this coupling constant equals to this one. This means that strong interactions between quarks, and it should be strong interaction, because that's what keeps quarks inside the hadrons, do not change this coupling, and it is the same as at hadron level. So let me write it this way. Strong interactions do not change vector couplings. So maybe I will again remind you that we have 3 quarks, and one of the quarks emit leptonic pair. But on the top of this there is very strong interactions between quarks, so they exchange, as you will see, gluons. But these interactions do not affect vector coupling, and it is the same at quark and hadron level. There is some analogy with electromagnetic interaction. So, suppose you have quark with a charge 230. And you perform measurement and you get that charge is 230. Let us switch on the electromagnetic interactions first. So if you switch on strong interactions, let us switch strong interactions immediately. According to strong interactions, U quark can emit gluon, which is neutral particle. So that's gluon. And gluon has electric charge 0. Now, if we will measure electric charge of this system, say put some detector, and this moment we will measure the electric charge. What we will get? We will get again charge 2/3 because this is neutral. So again this system will have charge 2/3. And this is because in this vertex we have conservation of charge. So what we will have, U will go to U, emit something neutral, but the total charge of the whole system again will be 2/3. So in spite of the fact that we have interactions, some additional interactions, the electric charge of this whole system doesn't change. It may be even more complicated, when U quark emits gluon, and this gluon decays into quark, transforms into quark-antiquark pair, Q bar. So this is kind of idea how strong interactions act. And again, if you will make measurements of electric charge, say in this moment, you will find that the total electric charge of the system will still be 2/3. Because here you have quark-antiquark, and therefore the total charge of all the system will be equal to the charge of U quark, original one. And so again you will have 2/3. Bottom line is the following. Although you switch on some new interactions, but because of conservation of electric charge in each of these interactions, total charge of the system doesn't change. So although you have strong interactions do not change electric charge of the quark. And for this reason, the electric charge of hadron, for instance proton, is just given by the sum of electric charges of quarks. And it doesn't change by strong interactions, by the fact that the quarks have exchanges of gluons. So this is important. That's clear, no? And this is, again, because of conservation of here is electromagnetic current and the electromagnetic charge. So electric charge is conserved, and as a consequence, strong interactions do not modify or as we are saying, do not renormalize the charges. So this is for the case of electromagnetic interactions and electric charges. That was hypothesis that probably vector current which enters here has similar properties as electromagnetic current. Both are vector currents. And so that was hypothesis, which then was confirmed. And actually, these charge currents and electromagnetic currents form kind of triplet of currents. That was current algebra in the early days in 60s, which actually elaborated all these concepts. But bottom line is the following. As a consequence of conservation of vector current, we have no change of electric charge due to strong interaction. And eventually we have no change of this weak charge, because in a sense this is weak coupling constant. This is analogy of electric charge. And so we have no change of a weak vector coupling. Okay? The second important concept concerns axial vector currents. So here we know what's going on, and we should put here 1. So this is the same as at hadron level. Now, how about these axial vector couplings, or these charges? So here important concept is partial conservation. Of axial vector current. And therefore partial conservation of the corresponding charge. And this is axial vector charge. And so, in this case we have GA not equal to GA at quark level. Here strong interactions change the axial vector coupling. So we have renormalization, as we are saying, of axial vector current by strong interaction. However, the change is not so big. It turns out that, remember, we had the GA equal 1.23 for neutron. And for quark, amazingly, this GA quark is 1. So this GA coupling constant actually depends on hadronic system. For instance, if we discuss some beta decays of not neutron but some nuclei, this GA becomes different. And this is actually very non-trivial and big issue even nowadays, to have the theory of this GA for different nuclei. It's also an important experimental issue, by the way. So, but what is really amazing, at least when we are using the simplest systems, that, and you can extract what is your GA, and it turned out that here we need to put 1. So, this is what you start at quark level, then you compute strong interaction corrections, that will lead to GA, which is not 1, but close to 1. It's 1.3. In some cases, it's even smaller. So this shows you that there are some renormalization processes, but not very big. It's just 20%. This is why we are saying partial. It's not complete conservation. If you would have complete conservation, then it would be also 1. So GA would be 1. Actually, it can be also smaller than 1 for some systems. So the amazing result is this. Again, that was theory of chiral perturbation theory I mentioned already, which actually allows to connect GA with pion decay coupling. Remember, we introduced coupling, decay coupling for pion meson and the mass of the pion. So there is a theory which allows to connect these things, and is very important to extract from observed value GA what should be GA at quark level. Of course, this is out of what we are doing here. If someone will work eventually on this object, then one can go into details. So we came to very important result. Without this, standard model would not exist. We have found that quark current has the same V minus A structure as leptonic current. Remember, we introduced leptonic current, and in that case, it was also 1 minus gamma 5 here multiplied by J mu. This is one of the bases of the standard model. So this current, quark current, has also V minus A structure. So conclusion is that at quark level, things are even simpler than at hadron level. At quark level, we have found that all charge currents have V minus A structure. Now we can write Hamiltonian at quark level, responsible for beta decay and other decays. So Hamiltonian of interaction is G and beta square root of 2, or just Fermi, and then the product of currents, G alpha. So we can put here D and G L, leptonic alpha plus Hermitian conjugate, and G D quark alpha is U gamma alpha 1 minus gamma phi D, and G L alpha is actually neutrino. So have this not conjugated, will be neutrino gamma alpha 1 minus gamma phi. Now let us consider pion decay, and I will stop at this point. Pion decay was described as transition of pion to mu minus, and if it is minus, to mu antineutrino. So this is the main mode of the decay, and also it was a decay into electron and electron antineutrino, but that was 5 orders of magnitude suppressed mode of the decay. Now, at quark level, pi minus is the system of U antiquark and D quark. And to organize this decay, we need to have the following: annihilation of this U bar and D, and emission of mu minus and mu nu. Agree? So it should be transition of D quark to U quark. And this is given precisely by the same current as here, as we use for beta decay. Remember, it was kind of not clear what should be the current which is responsible for pion decay. We just introduced in general. And remember, we use symmetry properties and Lorentz covariance to have some result for pion decay. Now we see explicitly what is this current. It was not clear at hadronic level, but it is clear what is the structure, what is this current at quark level. So, and what we observe is that the same current as is responsible for beta decay is also responsible for pion decay. So it's again the same transition of D into U. Okay, I stop at this point. Questions? So it's not just we need to introduce a new current to describe pion decay, but what we have realized when we move to the quark level, then it is the same transition of D quark to U quark, or vice versa, describe pion decay.
I have one question, so I'm not sure of something. We had that current with up and down there, but
Alpha, or just for covariance, and if you have conjugation, they are usually changed from up to down, the indices. Because you see here there's a conjugate, and therefore I put alpha index here, and this is down. And then you can check that electric charge is conserved and everything is okay. It's not just product of, it's not just product of these two. One needs to take into account this. And therefore it will be current, if it is D, it will be D here and U here. Okay, so it will be, so one current will change the electric charge by 1 unit, another to -1. And so Hamiltonian will have zero charge if there is no violation of electric charge. Sometime I can be, yeah.
My question was, for example, with neutron, we have the down quark decays into the up electron plus a neutrino. We can do the same in the pion. I mean, the down can go to the up, muon and neutrino, and then the up. I'm not sure if it can annihilate it with its antiparticle because we don't have like.
So here is particle. Here is annihilation of particle and antiparticle, right? Here we have a U antiquark and a D quark. Okay, so they annihilate. Eventually what we will see is that this annihilation is actually described by W. So you have eventually, when we go to deeper, like in a standard model, we have a mediator here, and so D quark annihilates with U antiquark and produce W boson minus. And then this guy decays into mu minus and antineutrino, muon. So eventually the structure of transition is like this.
Okay, thank you.
Okay, so we will continue tomorrow.
Professor, there is a question in the chat. The microphone doesn't work really well.
Sorry.
If you can see that, you can see the chat.
Oh yeah, not now. So I think it appeared, but I don't see it now. Now I can, let me check. Even 2 questions. So let me see if I will. Yeah. Okay. Pentaquarks or tetraquarks feed the picture I introduced today. So what's the problem? Now if we have a quark at quark level, say, let's take pentaquarks. And yeah, you have, say, 3 quarks. You may have like U, D, say, D bar. And so we have then that is 3 times 3 times 3 times 3, 5 times. That is in this type. The problem with these objects is that looks like proton and that looks like pi 0. And from experimental point of view, it was very non-trivial to establish what we have, some kind of collective system of these 5 quarks, or just pi proton and pi 0. But then some features actually indicated that precise measurements of mass, that it's more like the system of 5 quarks. So then I don't know what is, it fits. It's just high representations. So remember we discussed the product of quark antiquark, and then product of 3 quarks. But of course the question, can we have the system with 4 quarks, with 5 quarks? They become more and more unstable, by the way. So that's also, it's difficult to keep up and keep all these quarks together. Now the second question. Well, I think this is the same. Maybe the same question about pentaquark. Okay, so then see you tomorrow.